In this first example, we would like to show that the conclusion of the divergence theorem holds for a given vector field, this vector field here, over a solid region that's enclosed by a paraboloid and a portion of a plane. So let's start by drawing the region, and then we'll remember what the divergence theorem says. So here's a 3D coordinate axes, x, y, z axes. The paraboloid here is just standard paraboloid that opens upward. Okay, so this is opening upward in all directions, and it's, normal, standard sized, so to speak. And then here's our plane. We'll call this z equals 9, and this cuts off our paraboloid in a disk right here, right? And so the solid region is E, so the solid region is what's bounded in between here. We've got the surface, obviously, for the portion of the divergence theorem which requires a surface. And we've got this vector field, which we are given, right? We're given this vector field. And so remember what the divergence theorem says. It says that the flux of this vector field, so the double integral over the surface, so the surface is the boundary surface, of f dotted with ds, right? That's the flux integral. That this is equal to the triple integral over the entire solid region E of the divergence of this vector field, integrated up with respect to volume, right? So the divergence, which is why this is called the divergence theorem, of course. So let's put a box around this, all right? And then what we want to do in this example is compute both sides. Now, in general, you're not going to do that, right? You're going to choose the easier, you're going to verify that the theorem's hypotheses hold, right? And then you're going to choose the easier of the two to compute, because that's the benefit of having a theorem like this, that you can choose the direction that's going to work best for you. So let's start with the surface, though. With the surface, we have to actually treat as two different surfaces, right? So the surface number one is the graph of this function, and number two, we have to consider the plane. So the surface itself, S, is going to be built out of these two portions, the plane, which I'll call S1, doesn't matter which one you choose, right? And then the other portion of the surface, S2, which is just the graph of this function. All right, and so we need to compute the surface integral along each portion of this. Now we need to also make sure that our unit normal vector, our normal vector field is outward oriented. So to do that, let's first of all, for S1, we just need to make sure that we choose, up or down, right? So this is a plane whose normal vector is obviously the z component. That should be obvious here. And so for S1, we'll say that this is nu1, or n1, you might say. N1 we'll call it. This is just positive k, right? So this is just the vector 0, 0, 1. That's the outward pointing unit normal vector field. For S2, we need to compute the unit normal vector field along this graph of a function, right? And so what we can do is we can parameterize R2, we'll say, as the graph of the function, x squared, xy, and then x squared plus y squared. And then we compute the normal vector, and we'll just have to make sure that it's outward pointing, and if it's not, then we'll have to fix it, right? Just negate the whole thing. So I'm just going to call this r sub x, even though it's just for r2, right? But this is 1, 0, 2x, and then r sub y is going to be 0, 1, 2y. And when we cross these, we'll get our n2, maybe, right? Maybe. Let's just see. So when we cross this, we get what? We get negative 2x, we get negative 2y, and then we get 1. And so this is outward pointing. You can just, no, this is not outward pointing, I'm sorry, because you can just plug in the origin to this, and you see that when x and y are both 0, this points up into the surface, right? It points up in the z direction, and this should be pointing down in the z direction, away. So we want our normal vectors to point away from the interior, right, from the bounded region. And so this is actually negative n2, and our normal vector that we're going to use is going to be 2x, 2y, and negative 1 for the surface integral. Okay, so remember how surface integrals work. We need to compute this This is, by the way, should not be called n because it's not necessarily a unit normal vector field. It's nu. So we'll stick with it. It doesn't matter. This is just notational bookkeeping at this point. But the surface integral for us is going to be f dotted with ds. And so the way we compute this is we integrate over the parameter domain for each of these. So d of the vector field, plug in our components, right? So a vector field evaluated along the parameterization, so in the parameter domain, dotted with nu times dA at this point, because we have pulled back to the parameter domain. And what we need to do then is break this up into two portions, right? So we've got our double integral over S1 f dot ds plus double integral over S2 f dot ds. All right, let's do it. By the way, the domain for each of these is just a projection of the blue plane here, so that's when it intersects, right? So the domain D is going to be the domain x squared plus y squared less than or equal to 9. And so this can be treated in polar coordinates or something like that if we decide that that's appropriate. What we need to do now, though, is go back here and actually compute the surface integral, right? So this is our vector field. And let's see how this works. So I'm going to rewrite this vector field down here so that we can work with it. It's f equals, so it was y squared z cubed, and then it is 2yz and 4z cubed, z squared. I better make sure I copy that right. So 2yz, 4z squared. Okay? So, let's go then. We need to write down, let's just do the first surface integral first. So f dot nu ds. Nu here is just the unit normal vector k. So this one's going to be the double integral over that region D of this vector field dotted with k. So this just ends up being 4z squared dA. And this one, by the way, for this surface, remember S1 is the surface that's given by the equation z equals 9. And so z is just 9, right? So this then is equal to double integral over d of 4 times 9 squared dA. And so this is then just going to be, what, 81 times 4, which is, I believe, 324 times the area of D. And the area of D is, that's just a disk, right, of radius 3. So this is pi r squared, so 9 pi. So then we get 324 times 9 pi. So this portion of the flux gives us 2916 pi. All right, now we need to compute the second integral here. And for this one, we have to remember that our nu is this right here, 2x, 2y, and then negative 1. And so let's dot that with f to start with. So f dotted with nu 2, we'll call this. So this is y squared z cubed, 2yz, 4z squared, dotted with, remember, we changed the sign, so this was 2x, 2y, and then negative 1. 2x, 2y, negative 1. And when we take this dot product, we end up with 2x y squared z cubed plus 4y squared z minus 4z squared. All right, and then we also need to plug in the parameterization for R2. Remember, R2 is x, y, and then x squared plus y squared for the z components. All right, and so this one becomes 2xy squared times x squared plus y squared cubed. We're not going to multiply this out because we're probably going to want to go to polar coordinates for this one. So this is then 4y squared, x squared plus y squared, minus 4. We should just probably call this r squared from the beginning, but that's okay. So 4z squared is then going to be 4x squared plus y squared. Quantity squared, right? Quantity squared. And at this point, again, we want to compute the flux over S2. So we need to integrate this up with respect to area then. So this becomes the double integral over the parameter domain of all of this stuff. So I'm just going to write it like this, dA. And now we're thinking polar coordinates, right? So polar coordinates. So let's see what happens here. Remember polar coordinates, x is r cosine theta, y is r sine of theta, dA is r dr d theta, and r squared is equal to x squared plus y squared, etc. Right? So we have all these different polar coordinate formulas. What we end up with then is that we're going to have double integral 0 to 2 pi, 0 to 3. So the radius of the disk is 3. And then we have 2 times r cosine theta times r squared sine squared theta times r squared cubed. So we have r to the 6, 7, 8, 9. So r to the 9th times, this is going to be cosine theta sine squared theta plus 4 times, here we're going to have r squared times r squared, so r to the 4th times, this one is just going to be sine squared. And then minus 4, this is r to the 4th. That's it, right? R squared squared. So r to the 4th, so not too bad there. And then all of this, though, has to get multiplied by r dr d theta. All right, and so this integral is needs to be broken up into some parts here. We can do the r integral first and then see what's left, right? But we can break this up over the sums, and then each one of those is going to be separable by itself. So this one gives us 2 times the integral 0 to 2 pi cosine theta sine squared theta d theta times integral from 0 to 3 r to the 10th dr plus 4 integral 0 to 2 pi sine squared theta d theta times integral r to the 5th dr plus, this one is going to be, that's minus 4 integral 0 to 2 pi 1 d theta times integral 0 to 3, this one's r to the 5th dr. All right. And as we work this out, this one is going to be a u substitution, right? But as we look at this, this one's going to end up being 0, right? As you make a u substitution, you let sine of theta equal u, then these two endpoints have the same value. So this one is 0. So that one's gone. This one needs a trig sub, so this gets swapped out for 1/2 minus 1/2 cosine of 2 theta. Again, this portion is gone, and so we just integrate up the half. But the half, yeah, so that just becomes pi, right? So this is plus 4 pi, and then this one's going to be, this was from 0 to 3, right? So this one's going to be 1/6 3 to the 6th power. All right, and then on this one, we end up with minus 4 times 2 pi, that's just 1. And then same deal, right? So 1/6 r 3 to the 6th power. And now we notice that we have 2 copies of this and 1 copy of the same thing, right? And when we subtract those, we just end up with minus. This is going to end up being 2/3 pi, so 2 pi times 3 to the 5th power. So this ends up being negative 486 pi. And remember, our surface integral, we have to add in the flux, so the flux from the top of the surface, and we end up with 2916. So the total flux, the double integral over the entire surface of f dotted with ds is equal to 2916 pi minus 486 pi, and that is going to leave 2430 pi. So this is the flux as computed as a flux integral. All right. Now what we would like to do is check this by computing this as a divergence, right? Use the divergence theorem. Compute this as a divergence of this vector field over the solid region, and hopefully we get the same answer. So let's check it. So now we want to use the divergence theorem to compute this flux, right? And so the first thing we need to do is compute the divergence of our vector field F. All right, so let me just copy this vector field so that we don't have to write it yet again. And we will paste this down here. So just put this here. We want to compute the divergence of this, right? So the divergence of this is the x derivative of this first component, y squared z cubed, plus the y derivative of the second component, 2yz, plus the z derivative of the last component, 4z squared. All right, and you add all these up. So this is going to be 0 plus, this is just 2z, plus this one's going to be 8z, and we end up with just 10z. And so this needs to be integrated over the region E. The region E, that we just have to, we've already thought about this region quite a bit, so this is going to be best treated in cylindrical coordinates, right? So in cylindrical coordinates, this region E is bounded between the paraboloid, so the z direction, it's going to go from the paraboloid, r squared, up to 9, right? And then it's just going to go around the region D that we've already studied, right? The region D that we've already done. So let's see what happens down here. According to the divergence theorem, our flux is going to be equal to the triple integral over the solid region of the divergence of our vector field, dv, right? And so let's do it. This is going to be the double integral around D of the integral from r squared up to 9 of 10z dz dA. So I'm just breaking this up into a double integral of the single integral. We integrate this with respect to z, and we end up with, so we've still got our double integral here, we end up with 5 z squared, evaluated at these boundaries, right? So 9 and r squared dA. And so this is going to be integral 0 to 2 pi. Integral from 0 out to 3 for r. And then when we plug this in, we get 9 squared times 5, so 81 times 5. So we get 405 minus 5 r to the 4th. This is all times r dr d theta. This is, of course, separable. So we end up with integral 0 to 2 pi d theta times integral from 0 to 3 of all this, and this can be computed in two parts, right? 405r minus 5r to the 5th dr. And at this point, we have, by the way, maybe we shouldn't have even called this 405. Let's go back and call this 5 times 3 to the 4th, right? Because look at, we've got a 3 here. So 5 times 3 to the 4th. It's going to help us out. So as we continue here, what do we have? 2 pi times, take the antiderivatives here. So this one's going to be 1/2. So put parentheses here. This is 5/2. Again, let's write this out. We already know the answer, right? So let's try to think this through. So this is 1/2 times 5 times 3 to the 4th times r squared. R is evaluated from 0 to 3. Minus, then we have here, what? 1/6 times 5 times r to the 6th from 0 to 3. And we end up with 2 pi times, well, let's just make this 10 pi. Take the 5 out. Here we have 1/2 times 3 to the 6th minus 1/6 times 3 to the 6th. And 1/2 minus 1/6 is 2, so it's 1/3, right? And so this is 10 pi times 3 to the 5th. 3 to the 5th is 243. And so that gives us 2430 pi. There's the flux of our vector field across the surface. done as a divergence theorem, right? So there's the triple integral of divergence. There's what we got by doing it as a flux. These are the same. All right, so we have just verified